let us carry on with our discussion on fluorescence. Last class we started looking at the Jablonski diagram in some details, right. We talked about obviously we have talked about absorption before fluorescence. We started talking about fluorescence, and before going to fluorescence we talked about some of these non-radiative de-excitation pathways, right, like internal conversion, intersystem crossing, vibration relaxation, all these things, right. Now, just before I go forward, I will make a point and then come back to it later. So, the point is, if you would remember that the vibration relaxation occurs in a time scale of 10 to the minus 12 seconds, right. Now, that is much faster than a normal fluorescence lifetime, and I will show you just based on a very simple expression. The fluorescence lifetime is in the order of nanoseconds or so on an average, right. That means 10 to the minus 9 seconds. So, you can understand that the vibration relaxation would be happening much faster than a fluorescence process would be happening. That means the fluorescence de-excitation. So, then what would happen is, if you would just consider two states S0 and S1, right, not even S2, I am not considering S2 right now. So, if you would excite to a higher vibration level of S1, what will happen is, even before your fluorescence is happening, what is happening? Your vibration relaxation is happening. When vibration relaxation happens, vibration relaxation is occurring within the vibrational manifold of the excited state S1, right. So, how far will it relax? It will relax to a point where it is V is equal to 0 of the excited state S1. So, think about it, you have made some transitions like this to vibration levels, right, of the higher excited state S1, but when the transitions are coming from S1 to S0, in most of the cases, because of this time difference, what you are having is, or the time scale difference, what you are having is, they are coming from V is equal to 0 to different vibration states in S0. So, you can understand a small thing. The small thing is, initially it was taking from V is equal to 0 in the ground state to vibration manifold in the excited state. Reverse case, it is happening from V is equal to 0 in the excited state to the vibration manifold in the ground state. But because V is equal to 0 is less, I mean because V is equal to 0 has a lower energy than the excited V is equal to 1, V is equal to 2, V is equal to 3 of the S1 manifold or the excited state manifold, then what is happening is, you can see that you have already lost some energy, right. Because you have lost some energy, what has happened is, losing energy means you are going towards a higher wavelength, is not it. The moment you have lost some energy, now you can understand, if this was the absorption and this is where your fluorescence is happening. So, you always have a gap in between your absorption band and your fluorescence band, and that gap is referred to as what? It is referred to as the Stokes shift. That is what Stokes shift generally refers to, right. It is the gap between the absorption band and the fluorescence band. Okay. So, this can be explained based on the Jablonski diagram. So, that is what we just did right now. I thought I would just mention this, I will come back to this again, because we are on this diagram. Now, then we moved forward and we talked started talking about the lifetime, and we even came across, or even derived some expression. So, the expression last time we derived was, we started from something like this. So, last class we started from something like this, right. It was a, I said it was a delta function excitation. Delta function means it is a very fast excitation, that is essentially what you mean by that, right. And then coming from laser pulse, and this is how decay is occurring, Kr plus Knr, these are the two broadly defined general rate constants. Now, remember, when we are talking about Knr, then what I can write is, which I did not write yesterday, here I can write that Knr is the sum of the rate constant of all your non-radiative pathways, right, all your non-radiative pathways. So, just to make the point, I can write this as K IC plus K ISC plus whatever else you have. So, K IC is the rate constant for what? Internal conversion. K ISC is the rate constant for what? Intersystem crossing, and so on. If you have any other de-excitation pathway which does not lead to fluorescence or radiative transition, then they are clumped in Knr. Okay, then they are clumped in Knr. Now, we went on with this derivation, and finally we came to an expression like this. So, the expression looked like this, number 5, where the decay would be happening according to this exponential relation, and tau is given by 1 by Kr plus Knr. Okay. So, this is your fluorescence lifetime, and this essentially tells you the time it takes to go to 1 by E of its original fluorescence intensity. Okay, so fluorescence lifetime exponential relaxation time in this case is the 1 by E, the time it takes to reach 1 by E of its original fluorescence intensity, that is the one it started with at t is equal to 0, right. Okay, so this was tau for us, and then what we also said was we defined another parameter called phi f, which is the fluorescence quantum field, and we said that phi f is equal to kr over kr plus knr, okay, which is essentially the number of photons emitted over the number of photons absorbed. Okay, and this is a very important criterion or parameter. If you would be choosing a dye or if you would be choosing a fluorophore for anything, this is something you will have to have the information about. You have to have it in your hands before you can go ahead and do an experiment, because this is one single parameter which is possibly of utmost importance or the most importance for a fluorophore, right. Now, let us move forward from here. So, what I will write down is, if you remember this tau, the way we defined tau was 1 by kr plus knr, right, but there was also another tau we defined before. Do you remember? So, that tau was tau radiative, which is essentially tau r. What was it equal to? 1 by, was not it A to 1, where A was your spontaneous emission coefficient. So, that was the tau radiative, okay, no stimulated emission here, right. So, then what I can write is, kr is equal to 1 by tau radiative, okay, kr, that means k radiative is equal to 1 by tau radiative, kr being the rate constant for the radiative process. Now, this can be further written like this, okay. Now, remember what was A21? When we considered A21, we said it is a spontaneous emission from excited state 2 to excited state 1, but see, that time we were starting our discussion on spectroscopy, and we did not consider any other levels. What we said was only state 1 and state 2, but now you know even if you have electronic state 1, electronic state 2, within that state you will be having many vibration levels, right. So, then when we are talking about A, it should not only be 2 1, what it means is it should also be from the respective vibration levels of excited state 2 to respective vibration levels of excited state 1. So, then what we should envelope or we should have is the envelope of all the transitions that is happening from the excited state to the ground state, right. So, then what you do is you do a summation, that means your summation of all rate constants you have. So, the way you write is very simple, you take a summation over what. So, this is A, and remember we just described or we just discussed that because vibration relaxation is much faster than your fluorescence, then most of the emissions would be taking place from what, the V is equal to 0 state of your upper excited state, which is S1. So, what I can write is, if A is the spontaneous emission coefficient, I can write it is coming from upper state to lower state. So, I can write U, which is the upper electronic state, U, then I write 0. What does this 0 mean? That means the 0 vibration level of the upper electronic state, right, and then you are going to lower state, right, the lower electronic state, but in this lower electronic state you can have a series of vibration levels, then you write M, okay. So, you can see what is the parameter which is now varying for you, or the summation is over what, M, because U and L are just upper and lower states, 0 is defined for you, okay, and this is what it stands out to be. So, are you clear about this expression? So, essentially what it means is, it is the spontaneous emission coefficient of whatever transition you have from your ground vibrational state in the upper electronic state to the vibrational manifold of your low electronic state, right. Okay. Now, this is proportional to, now also remember this, if you are talking about spontaneous emission, whatever emission is going to happen, it is going to depend finally on the vibrational overlap integral, remember that Frank-Condon overlap. So, if we have the way we had defined Frank-Condon overlap, if it was the probability of a transition happening, say absorption, fluorescence is essentially also the same thing, right, just the reverse of that. So, then in this case also that one should play a role, that means your A should be having a relation or should be in a certain way proportional to that transition probability or transition moment. So, then what you can write is, there is a proportionality relationship, we will not look at that, but we will just write is that this is proportional to psi L, then mu psi u squared. Okay. Just with a small change, if you would have remembered the way we had written this transition moment integral for absorption we were going from the ground state to the upper state, right. That means the lower state to upper state. So, your operator was acting on what? The lower state. So, in that case what we had is what we had the mu, and the extreme right we had what? Psi lower, and then we had psi upper because it was going to psi upper. But now you are talking about the reverse process. So, what do we have is you have mu, then the extreme right it is operating on what? Psi upper, and after that it is going to psi lower, which is coming here, right. So, this is the way it is normally represented. Now, you can understand why it is the way it is represented is the final state comes before, then the operator, then initial state, right. Now, initial state for absorption is a ground state, for de-excitation or the other way emission is your upper state. Okay. And the reason this happens is because, say for absorption, if you take the example of absorption, only after your operator operates on the ground state do you go to the excited state, and you know the operator acts on what? Not to the left, but to the right of it, and that is the reason why you maintain this arrangement, rather this sequence in the integral. Okay. So, this is how it is maintained. If people are talking about transition moment integrals in spectroscopy, please stick to this. You will not get wrong if you revert it. It's not nothing is going to happen, right. But it's just that it's good to go by the fundamentals. So, that means you understand how the process is happening, right. So, again you can see that this is proportional to this square, and if you remember that Frank-Condon overlap, the square was the Frank-Condon factor, and that determines the intensity of the transitions. The same thing is going to happen here. Okay. So, that was one, and the next thing is will not derive it, but I will just give you another relation. So, what I can write is the tau radiative, it can be derived from whatever we have, is generally or approximately can be written as 10 to the minus 4 by epsilon. Okay. And this is max. So, let not writing any equation numbers, but if I write this to be 1, this to be 2, this to be 3, then I can write this to be 4. So, what it is telling you is that the radiative lifetime can be approximately calculated as by this ratio, which is 10 to the minus 4 over epsilon max. Epsilon max is what? Epsilon max is the maximum extinction coefficient to have for a given molecule, right. Now, this is for you just to estimate, even before you do something, if you know the epsilon, what the fluorescence lifetime might be. I am not saying that it will be this, because remember this is tau radiative. You always have competing pathways. What do you have? You have the non-radiative transitions, and you never measure tau radiative. What you measure is actually the tau, which is equal to 1 by Kr plus Knr, because non-radiative transitions are always there to a certain extent, depending upon experimental conditions, depending upon the molecule, depending upon your solvent conditions, right. Okay. But anyway, just to have the flavor of it, because I said that vibration relaxation happens in the minus 12 seconds, this one happens sorry, the fluorescence happens in about 10 to the minus 9 seconds. So, you can see if epsilon max lambda says 10 to the power minus 5 mole inverse centimeter inverse, okay. If that is what it is, then you can see the tau radiative would be equal to what? Sorry, this would be 10 to the power plus 5, make it plus 5, then it should be 10 to the power 9 minus 9 seconds, so 1 nanosecond. Okay. So, this is just an approximate, I mean this is a ballpark idea, this can be derived, let me tell you this can be derived. Okay. We are not just going to the derivation, based on certain equations this can be derived, and that is how you know that a fluorescence lifetime is typically in the order of a nanosecond or so, okay, without doing any experiments, right. So, this was what you need to know about fluorescence, at least in terms of the de-excitation pathways and all these things. Now, listen, there is one more thing possibly you guys would realize when you are doing any experiment, say you are doing fluorescence experiment I am talking about, because here we are discussing fluorescence. When we are doing a fluorescence experiment, no matter what you do, depending upon the solvent, you always have some dissolved oxygen in it. Okay. Now, oxygen is a quencher of your fluorescence. Okay. It is also a quencher of your phosphorescence, but since we are discussing fluorescence, let us stick to that. It is a quencher of fluorescence. Now, what will happen is, so when I wrote before d of 1 a star over d of t, so what we wrote was k r plus k n r, right. That these are the two ways it can depopulate, that means excited state can depopulate. But now think about this is another factor. Suppose your solvent has dissolved oxygen on the order of millimolar level, right. That is typically what it is in some of your solvents. Then what will happen is, this oxygen would collide with the fluorescent molecule. The moment it would collide with the fluorescent molecule, it would take away some of the energy, and those photons, rather that energy will not be available to you in terms of a radiative photons, right. That means you are losing those photons in a separate non-radiative pathway. This non-radiative pathway is coming because is due to the collision of oxygen with your fluorophore. So, this is here oxygen is referred to as something known as quencher, that means it quenches the fluorescence of your fluorophore. So, therefore, if you have dissolved oxygen, I can write it as plus k q times concentration of q 1 a star, where q is the concentration of quencher, and here we are talking about dissolved oxygen as a quencher. Okay. Here we are talking about dissolved oxygen as quencher. Okay. So, that means apart from Kr and Knr, you have another rate constant which is coming in. So, now what will the fluorescence quantum yield be, the expression? It will still be the same, only with what, Kr over Kr plus Knr plus Kq times Q, is not it, because this is the extra process you have, and simple, it is Kq times Q because you have the rate constant which depends upon the concentration of oxygen, right. That is why you have, and Kr plus Knr always in terms of time, that means inverse of time. So, Kq, what is the unit of Kq now? Obviously, it would be time inverse, that means second inverse or whatever. What is the other? Concentration inverse too, right, because dimensionality has to be maintained, and that is why you have Kq times Q. So, the concentration cancels out. Okay. So, you can now realize if you have an additional collisional quenching term, what would happen is quantum yield would further decrease. Okay. Now, this brings us to a very important point. The point is that your dissolved oxygen obviously is always there. So, the way what you can do is you can try to remove dissolved oxygen, that means you can purge your sample solution with argon, nitrogen or whatever and try to remove that. Okay. That is one way of doing it. Now, I am not sure whether you have heard of this concept of fluorescence quenchers. So, there are some compounds which are quenchers. Now, we have talked about one type of quenching, not exactly in terms of quenching, but in terms of intersystem crossing. We talked about effect. What effect was that? We talked about heavy atom effect, right. Now, heavy atom effect, remember there were two types, one was internal means iodide, rather this was a part of the molecule itself, and the other one was external. External means it was with the solvent, right, like iodoethane or something like that we said. Now, similar to that, but not exactly similar, suppose you have a fluorophore, in a solution, right, and you add potassium iodide, right, and let me tell you that the fluorophore is a charged molecule. Okay. Now, when you add potassium iodide, what will happen is potassium iodide is also charged, and say the fluorophore is positively charged. So, this iodide will have an affinity for the charged species anyway. Now, you also know that iodide favors what? Spin orbit coupling. So, it will favor what? Intersystem crossing, and the more it favors intersystem crossing, what will happen? What will happen is the fluorescence quantum yield would decrease, right. So, essentially that is what happens is that you can use iodide as a fluorescence quencher. So, here we talked about oxygen, but exactly in the same way other fluorescence quenches, so other one is your iodide ion. So, people use potassium iodide. The other one is a compound known as acrylamide. The other one is a compound known as acrylamide. Okay. So, these have been these are very commonly used quenches. You can understand a difference. Iodide is charged, right? Acrylamide, by the way, is neutral, it is not charged. So, if you have a scenario where you do not have much charge interactions out there, that means you are talking about an environment, say a protein, where the interior is essentially hydrophobic. So, because it is nonpolar, iodide would find it very difficult to access the interior of the protein. So, if you would like to look at a quenching of a tryptophan residue which is in the interior of a protein, you would not use iodide. What would you use? You would use acrylamide, because acrylamide does not have a charge, it is neutral, and in that sense it would possibly having a little more accessibility to or for the tryptophan or for the fluorophore inside the protein hydrophobic site. Okay. So, this leads to a completely separate chapter on quenching. And this can be referred to as Stern-Volmer kinetics or plots. Stern-Volmer kinetics or plots. Okay. Right, I mean just know this, we will not discuss it right now. Okay. So, now let us go back to the slide. We have talked about fluorescence at a bit. Let us talk about the other radiative process, which is phosphorescence, right. So, we are talking about phosphorescence now. So, it is a radiative de-excitation from T1 to S0, right. The transition is spin forbidden, but spin orbit coupling again allows the transition to happen, right. The radiative rate constant is very low, remember it is forbidden, right. So, the radiative rate constant is low and hence is very prone to de-excitation by non-radiative means. Now, try to understand the significance of this. We just said that a fluorescence lifetime is on the order of nanoseconds, so in the -9 seconds. Now, let me tell you, if you remember the table which we had discussed last time, the phosphorescence lifetime is in the order of microseconds or so above. Okay. So, you can see there is a huge gap between fluorescence and phosphorescence. So, which state is long lived? Is it fluorescence or is it phosphorescence? Phosphorescence is. Now, suppose you have these two states, right, hypothetical situation, you have a fluorescence and you have a phosphorescence, right. You know that this one is going to come down first and then this one would follow. Now, I take this in a system where I have many quenchers available, say oxygen, right, or any other quencher which would quench both, oxygen quenches both. Now, tell me which one would be more affected? Well, how many of you are for phosphorescence? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Man, and the rest are for fluorescence, because the rest is the other half of the class. Okay. You know, this is a collisional quenching with oxygen, so it will depend upon diffusion, right. If you remember that Smoluchevsky's diffusion relation, what we had said. So, it is typically in the order of nanoseconds, remember it is typically on the order of nanoseconds, right. Okay. The collisional quenching constant, rate constant. So, you think about this, your fluorescence has almost the same rate constant as that of your quenching. Okay. So, depending upon which one happens faster, if fluorescence is happening faster than the quenching, then quenching will not be able to affect it that much. If the fluorescence is slower than the diffusion of the quencher molecules, then obviously fluorescence will be affected. So, that means in fluorescence you have a chance of it not getting that affected, but it will get affected, but not getting that affected, because now you are competing between two similar rate processes, right, to start with. But think about phosphorescence now. Does phosphorescence have any other option? It starts from microsecond because it is always there, right. So, no matter what it is, your quencher molecule is always going to hit the molecule, the phosphorescent state, before it can come back. So, essentially what it does is it decreases the quantum yield of phosphorescence. Do you understand why now? It decreases the quantum yield of phosphorescence because it is longer lived, and because it is longer lived, it is more prone to collisions with what? Your quencher molecules. That is why phosphorescence is actually very hard to have a very high quantum yield of phosphorescence. This is the reason. If you have to have a high quantum yield of phosphorescence, there are two ways, a couple of ways you can do it. One is you reduce the diffusion, that means say you go to higher viscosity, or you remove the quenching molecules by some way, by bubbling gas or some way or the other. Okay, so that is why phosphorescence is always more affected as compared to fluorescence. Okay. So that is what we meant by this. So that is now this is the other thing I was telling you. Phosphorescence quantum yield can be increased at low temperatures or rigid medium where collision rate is reduced. So essentially, if you reduce collision rate by one way or the other, then you can increase the phosphorescence quantum yield. Okay. One more thing. So that was phosphorescence for you. Let us talk about the Stokes shift, right. So this is what we said. We said that you have these. This is excited state, this is a ground state, right. You do excitations, so it goes from the ground state to here. Okay. So this is the absorbing energy, so which is nu A, say. So it is nu A, nu A means in wave number, okay, your energy of absorbance, but then before it can come down from here, what it does is it does a vibration relaxation to here, and then it starts coming down from here. Okay. So you can what has happened is you can already see that this energy nu A is higher than nu F. So then what will happen is there will always be a gap between your absorption maximum and a fluorescence maximum, especially in the condensed phase. If you go to the gas phase, see, you would not be having these many interactions. So vibration relaxation would be reduced and they would be far closer to each other. Okay. So the Stokes shift arises from the fact that you have a rapid vibration relaxation before the molecule can come down to the ground state from the excited state. Okay. And that is why this, you can see this difference as it is said here at the bottom is referred to as your Stokes shift. Okay. And generally Stokes shift is referred to in terms of wave numbers. Okay. Because Stokes shift always has something in terms of energy, and I will tell you why. I will tell you why, because where did you hear Stokes shift from first when you were doing spectroscopy? Did you hear it from fluorescence or did you hear it from something else? Raman, right. You have Stokes lines and anti-Stokes lines. So Stokes lines is what? Stokes lines is where it moves to a lower energy as compared to your Rayleigh scattering. So that is essentially how Stokes comes around. So your emission is always at a lower wavelength than your absorption, right. That is your Stokes shift. That happens because of this. Now there are many other reasons why your emission can be at a much lower wavelength than your absorption, right. Now anyway, this is the difference. This is the one you always have to keep in mind. Okay. Now if I give you an example, well, first the Stokes shift is the gap between the maximum of the first absorption band and the maximum of the fluorescence spectrum expressed in wave numbers. That is what I said. Now if the dipole moment of a fluorescent molecule is higher in the excited state than in the ground state, the Stokes shift increases with solvent polarity. Okay. Now just keep this in mind. I will show you a diagram where you would understand how solvent affects fluorescence, and then you would see that how this Stokes shift will depend upon the polarity of the medium, right, because Stokes shift will not be constant, it will depend upon some factors, one of these factors being the solvent polarity. So as I said, it is used in the estimation of polarity of the corresponding solvent. So for example, if you would take a fluorophore, you would take it in solvent A and solvent B. If you take in solvent A, if you would see that the Stokes shift is small, and in solvent B if you see the Stokes shift is huge, then you would say that the solvent B is more polar than solvent A, and that is how you can estimate it. Okay. And there are other scales too, right. So this is an example. So this is of a derivative of this compound, it is called benzoxazinone derivative. Now you can see out here the absorption is at 488, right, this is the absorption out here, and this is the emission peak at 590 nanometers, and the Stokes shift is of the order of 3540 centimeter inverse. That is not bad, that is pretty huge. Try to realize this, what will happen is, this is a case where your fluorescence is pretty well separate from your absorption spectrum. Okay. So, suppose you are going to excite somewhere here, say suppose you are going to excite here, right. That means you have excited this benzoxygenone derivative BOZ7 at this 480 nanometer, right, because here it absorbs the most. Now, because you have excited it, now you can see effectively you can collect the fluorescence, from any point say only the fluorescence, which is exclusively fluorescence, from any point say here, because here the absorption is tailing down. But keep one thing in mind, there is, in this case there is a small overlap between your absorption spectrum and your fluorescence spectrum. Can you see that? So, this is the absorption spectrum which is coming down, and this is your fluorescence spectrum. So, this shaded area is the overlap between the absorption and the fluorescence spectrum. Okay. Now, this is a huge consequence when you especially have, you are doing fluorescence resonance energy transfer and all these things, because this really matters. But anyway, the point is that instead of this, if you had a compound which had a smaller Stokes shift, right, what would happen? Suppose you take another benzoxygenone derivative which is still absorbing at 488, but it has a smaller Stokes shift. So, where will it go? So, this one would move on this side towards this side, right. Because it would move towards this side, what would happen? A larger amount of fluorescence would overlap with your absorption. Now, that is always not welcome. Okay. Right now I cannot go into the details, but this is just the, these are just the ramifications of having a larger Stokes shift or a smaller Stokes shift. Okay. So, what are the factors affecting fluorescence? One is the rigidity of structure, the other one is temperature, solvent effects, polarity, viscosity, dissolved oxygen, this we have discussed, pH, concentration, and many other factors. Okay. But these are the broadly defined factors that we can look into. If you look at the first one, the rigidity of structure, look at these two compounds, one is biphenyl and one is fluorine. Okay. Now, before giving you the answer on the slide itself, tell me which one is supposed to have a higher quantum yield, the first one or the second one? Second one. Any other thoughts? Well, the other thought will be the first one anyway, right? No one going for the first one? None. Okay, excellent, all of you are right. Now, tell me why. More rigid. Well, it is rigidity of structure. Okay, it is more rigid. Okay, then what happens if it is more rigid? Huh? Conjugation will be more, but it is not about conjugation I am talking about, it is about something else. What is the difference between a flexible molecule and a molecule which is rigid? Think about in terms of your de-excitation rates. Which one is more fluxional, which one is more flexible? Biphenyl. So, it will move a lot like this, right. So, because it will have a large amount of motion, it would be having higher chances of colliding with some other stuff. Because it has higher chance of colliding with other stuff, which one would have a higher chance of coming down without radiating photons? The biphenyl one, that means the one which is more flexible. The one which is rigid does not have too many ways to go around, right. So, it is pretty much stuck. So, this is your rotational mobility essentially you are talking about, right. This is what your rigidity of structure is. So, as you said, the biphenyl has a fluorescence quantum yield of about 0.2, fluorine has a fluorescence quantum yield of what 0.7. Okay. So, this is one very important factor. So, that means if you would take two molecules of similar structure, one which is more flexible than the other, even by closing your eyes without doing an experiment, you can say which one would be having a higher quantum yield and which one you would rather take for doing some fluorescence studies if you have to use one of those. The next one is the effect of temperature. Now, what do you think the effect of temperature would be? Would it increase the fluorescence quantum yield or would it decrease? It would decrease the fluorescence quantum yield. Why? Because with temperature what will happen? Right, your collision frequency would increase, right, that is exactly what happens. So, increase in temperature in general results in a decrease in the fluorescence quantum yield and lifetime, because non-radiative processes influenced by thermal agitation, which are collisions with several molecules, intramolecular vibrations and rotations, are more efficient at high temperatures, right. Now, phosphorescence, look at this sentence. Phosphorescence is more strongly affected because of the long lived triplet states which are efficiently deactivated by collisions with solvent molecules, right. Now, you can understand, as we were discussing before, which one is more affected, phosphorescence or fluorescence? Phosphorescence, because phosphorescence is more long lived, right. So, if you have to increase the quantum yield of phosphorescence, what you would do is this. If molecules are in a frozen solvent or a rigid matrix, okay, that means they are not moving around a lot, collision frequency is decreased, you decrease the temperature. You decrease the temperature, what will happen is, you can see by cooling, that means decreasing the temperature, the phosphorescence quantum yield can be increased by about 1000 times as compared to fluorescence which is only affected about 10 times or more. So, right. So, this is how phosphorescence is much more sensitive to your temperature quenching, right, or even other collisional quenching as compared to your fluorescence, just because of the fact that it occurs at a much later time. It is a delayed radiative process. Now, oxygen quenching, as I said, can be avoided by bubbling nitrogen or argon in the solution. The most efficient method used particularly in phosphorescence studies is to perform a number of freeze pump thaw cycles. That means, you freeze the solution, you thaw it, you freeze it again, you thaw it, you do it 4 to 5 times, and that is one of the best ways of getting rid of all dissolved gases you can have in the system, and then you use it. Okay. Now, this is also something which is normally done for especially done by groups who really have to worry about this oxygen quenching, right. Okay. Now, the solvent effect. I was talking about the solvent effect. See what happens. Suppose you have a ground state molecule, right. So, this is a ground state molecule. Now, do not worry about the excited state right now. This is a ground state molecule. Say your solvent molecule you have taken as a dipole, right. So, the way at equilibrium, before doing any excitation, your water molecule, say you have taken it in water or any solvent, your solvent molecules will also orient themselves along with the dipole to stabilize the system, to give it the lowest energy. So, that is your ground state electronic energy, right, along with the vibration levels. Now, think about this. The issue is, you make a transition. The moment you make a transition, you bring about electron redistribution, right, and in many cases there is a large enough change in dipole moment. Say for example, if you take tryptophan, which we have talked about, you have heard about a lot, tryptophan has about a change of 4 to 5 dBs when it goes from the ground state to the excited state, it increases. Okay. Now, because it increases, tell me, the ground state there was not much of a charge separation. Now, the charge separation is increased in the excited state, right. Now, because it is increased in the excited state, now see what is happening. When it increases, when it is excited, the solvent molecules have not been able to respond. Why? Because this was 10 to the minus 15 seconds, and we said the nuclei follow much later than the electronic excitation. Now, you are talking about solvent molecules which will be even later, right, because these are kind of much heavier than the electron. So, but because you have given rise to a non equilibrium situation, what will happen is the solvent molecules will finally equilibrate to the new situation and solvate it. Now, the way you solvate it is, because it goes up like this, this is your absorption, remember, this is your absorption which has happened before any solvent reconfiguration has taken place, right. But after equilibrium, this level slowly comes down here. Why? Because you have a charge separation, the solvent molecule depending upon the polarity of the solvent, say if it is water, it will reorient to stabilize this and it will decrease the energy of this electronic state. Now, this is the equilibrium at the electronic state, that means after your solvent reorganization has taken place. Are you with me up till this point? So, you understand. So, here when no solvent relaxation, no solvent reorganization, the energy is pretty high. After that, the solvent stabilizes the excited electronic state which has a change in dipole moment, it comes here, right, because this polar interactions. So, now tell me, your absorption was from here to here, your ground state has not changed, okay, just keep it like that. This one has been stabilized more, right. So, what will happen to the fluorescence now? Is it of high energy or low energy? It is of low energy, right. Now, remember Stokes shift, I said it will also depend upon solvent polarity. So, what would happen? Depending upon the solvent polarity, the more polar the solvent is, the more it will stabilize this electronic state. So, the more it will come down to a lower energy. The lower the solvent polarity is, the less it will stabilize the electronic state. So, the higher the energy of that stabilized state would be. So, that means the solvent polarity would be having a telling effect, a defining effect on the observed Stokes shift. Is it clear or not? Okay. So, that means solvent polarity is a very important issue. That is why you will see that if you take dyes, especially if you take tryptophan, I will show you tryptophan, that is how we will end the class. You would see that if you change solvent, say if you take a dye in say hexane, which is a non-polar solvent, you go to water, which is a very polar solvent, you will see that Stokes shift, that gap between the absorption and fluorescence has changed a lot, right. Then in many cases, remember, absorption spectrum is not that affected, in some cases it is affected. Okay, so that thing you also will have to keep in mind, but whatever discussion we are having right now is we are taking the assumption that the absorption spectrum is not affected that much. Okay. So then that is what I said. So you can see here, initial equilibrium situation, your solvent dipoles were reconfigured in equilibrium along with the molecule dipole. You go to the excited state now, it says here the excited state fluorophore, this is the excited state fluorophore, its dipole direction has changed, you see, okay, because it is a new dipole, it is in a different direction, but the solvent molecules, because they are massive, they have not been able to respond to it, they are still pointing in the same direction. So it is a high energy state, it is a non equilibrium situation. Now what will happen is, you have given time, the solvent molecules will try to reorient. So now you can see this is the next stage where it is fully reoriented. So the energy has decreased. Now this process is referred to as, you can see out here, it is referred to as something known as solvent relaxation. Okay. This is a very interesting topic. Okay. It has been, I mean, people have looked at it like anything, people are still looking at it. So solvent has brought down the energy of the excited state, the initial excited state, to a lower energy level, and now your fluorophore is taken from here to the fluorescence to the ground state. So this difference, which is your Stokes shift, then will depend upon your solvent polarity. So this is how your fluorescence spectrum is affected because of solvent polarity. Okay. Now the other thing is viscosity, your fluorescence can be affected by viscosity. How would viscosity play a role? Viscosity would possibly increase the quantum yield. Why? Because it would decrease the collision rate, right. So that is how viscosity plays a role, right, and very simply speaking. Okay. Now let us end the class by looking at some of your protein fluorescence, right, and so that you can have some feel about how people use these things in their biophysical studies. Now this is, you know, I have generally taken these pictures from these figures from this book on fluorescence spectroscopy by Lacquevis. This is a really good book. If you are interested in fluorescence, you should definitely have a copy of that and look that up. Now what you can see here, this is a tryptophan fluorescence. On this side is your absorption spectrum, which is epsilon to the left, times 10 to the power minus 3. That means whatever epsilon value you have in terms of, remember what was the unit, mole inverse, centimeter inverse, wasn't it, right, that was the unit, times 10 to the minus 3. So if you look at the 280 was the peak, right, of tryptophan. So say if this is 280, I don't know what is 280, I guess this, say this is 280 nanometers, you can see it corresponds to something close to 5. What was the epsilon max of tryptophan? Do you remember? Wasn't it 5500, 5600 or so? So that means here it is kind of 5.6 times 10 to the power 3 times 10 to the minus 3, which is giving you 5.6, right. So that is why it says epsilon times 10 to the minus 3. Okay. Now this is your spectrum, absorption spectrum. Now look, this is the emission spectrum. This is emission spectrum of tryptophan in water at pH 7 equal to 7. Okay. Now immediately you can realize, can you see the shift between the absorption maximum and the fluorescence maximum? Okay. So this is essentially your Stokes shift. Okay. Good. Now let us look at the other one. This is tyrosine. Tyrosine, the absorption maximum was where? 274. Okay. So this is epsilon, it is written out here. Now you can see here, if you would observe properly, the Stokes shift of this is actually not as high as that of tryptophan, right, and possibly you can understand that I said tryptophan has a high dipole moment change of about 4 dBi units, 5 dBi units. Tyrosine might not be having that much of a change. So that is why the Stokes shift might not be that large, right. But anyway, so this is the fluorescence of tyrosine when you are exciting in the absorption spectrum. The other one is phenylalanine. Okay. Now one thing you can realize, phenylalanine is not used that much because first of all its epsilon value is really low and its fluorescence quantum yield is also not that high. Okay. So, I forgot to write down the fluorescence quantum fields out here, but for tryptophans in water it is like 0. It is close to 0.2, 0.15, 0.16 like that. Okay. So, it has the highest among all the amino acids, right. So, these are the 3 typical fluorescence spectra along with the absorption spectra of the amino acids that we are concerned with when we are talking about spectroscopy of proteins. And remember, these are parts of your protein. So, these are called intrinsic fluorescence. Intrinsic fluorescence means it is already a part of the protein, it is internal to the protein, you do not have to add fluorophores from outside. Okay. Now, let us take this case. Remember, we talked about solvation. When we talked about solvation, what did we talk? We talked about the polarity of the environment, right. And if you are talking about the polarity of the environment, now think about the situation. You are given 4 proteins. In one protein, I do not know whether it is visible, in one protein you have a tryptophan, the red one is a tryptophan. In one protein, so in number 1 the tryptophan is buried, you can see it is very much inside the hydrophobic core. So, that means it is inside and it is surrounded by all the protein residues. So, it is not actually it is not accessible to water because it is inside. Now, if it is not accessible to water, then what is the interior environment? Hydrophobic. Okay, good. Now, look at number 2. So, here this is number 1, this was number 1, you can see it is very much sitting in the interior. Let us look at number 2. So, number 2 is a little less buried than number 1. So, this is what we are talking about, this is number 2. Now, look at number 3. Number 3 is kind of on the interface, a part of it is buried, a part of it is not buried, right. So, this is number 3 and number 4, what is happening? Is fully open. So, you have 4 situations where you have 4 different degrees of polarity, right. The buried case has the lowest polarity because it is mostly hydrophobic, right, almost fully hydrophobic. The open case, which is fully exposed to water, is the one which is facing the most polar environment, right. So, then if you think about that Stokes shift, think about the Stokes shift, which one would be having the highest amount of Stokes shift? 4, and the one which is lowest would be number 1. So, let us hope this is maintained when you do an experiment, right. So, let us look at the spectra right now. Now, see, does it follow what we had predicted? Look at number 1. Number 1 is the one which is most buried, right. This is the one which is the lowest wavelength. What does it mean by lowest wavelength? Means highest energy. That means the energy gap between the ground state and the excited state. That means the relaxed excited state is higher, okay. And 4 is the one which is the lowest. Okay. Also, if you try to realize one thing, because we are already here, though we are not talking about this feature of the spectrum too much, but tell me another very important difference between say 4 and 1 looking at the spectrum. Broadening, very good. What is this broadening due to? Huh? Direct exposure. So, direct exposure to solvent molecules, right. So, now you can understand that because it is in 4, because it is so exposed to solvent molecules, you will be having so many different types of interactions, hydrogen bonding interactions and all these things, hence the number of different transitions would be a lot higher and hence the spectrum becomes broad. So, this is called broadening, okay, this is called broadening. And obviously, if the same fluorophore is inside in the interior of a protein, or rather it is in the interior of a protein, then it would not be accessible to the solvent molecules. So, you would not be having that many collisions with the solvent molecules and hence its broadening would be less, okay. So, that is typically how a fluorescence spectrum would vary, right. If you take a tryptophan in the interior of a protein and if you take the tryptophan and put it on the surface of a protein, this can easily be figured out, okay. Now, guys, think about this. Suppose I start with a protein where the tryptophan is in the interior, like a case which is 1. So, that means it would be having a very blue shifted fluorescence, that means a fluorescence which is at a low wavelength, okay. Now, I start denaturing the protein. When I start denaturing the protein, what am I doing? I am slowly opening it up. If I am opening it up, what is happening to this fluorophore? Is it getting more exposed or less exposed to solvent? More exposed. So, if it is getting more exposed to solvent, what is going to happen? So, it is the fluorescence maximum is going to shift, it is going to go over towards the red side. So, this is typically what you would see if you would take up any protein. Okay. So, that means if you are unfolding a protein, this is a general case, if you are unfolding a protein, this is what you would observe. Okay. So, see this is what you observe here. One is this is a protein called azurin, right. There is a protein called azurin. So, you can see there is a 1 tryptophan here, 1 tryptophan protein. This protein azurin in its native state. So, this is the native state. In its native state, what has happened is, you can see it was very similar to what we had before. It is close to what, like 305 or so, something like that. But the moment you denature with 6 molar guanine hydrochloride, see how much it has shifted by. It is shifted by a huge amount, right. Now, guys, remember all those soft flow kinetics we talked about, and we talked about a certain change in signal, spectroscopic signal, right. Now, think about the kinetics and think about an experiment you are doing. Suppose you are looking at the refolding of azurin, right. If you are looking at the refolding of azurin, you can do it in 2 ways. 2 ways you can do it is, that means when azurin is fully unfolded, say in a high concentration denaturing, its emission maximum would be close to what here. So, this is about say 352 nanometers or so. Now, the moment you refold it as a function of time, what would happen to this? This intensity at 352 would decrease, because it is moving slowly to the left, right. So, what you can do is, you can monitor this change in intensity at 352 nanometer of the protein as a function of time. That means, you mix it by stop flow, continuous flow, whatever, and then you tell your detector to monitor the change in intensity for me at 352 nanometers, because that is where the unfolded state was. So, what will happen is, its fluorescence as a function of time at 350 nanometer would decrease, right, and the last point it decreases when it reaches equilibrium, that means you have reached the folded state. What is the other way of looking at it? Observing the, so the other way, right. So, the other way is I can look at this one, is not it. One is I looked at the decay or the decrease in intensity at the denatured state fluorescence. The other way is I can look at the increase in fluorescence intensity of the folded state, which is at 305. So, in that case your fluorescence intensity would increase and then finally stop when you have reached. So, this is exactly what people do, right, and that is why you have to know fluorescence before you can do that, because you have to know at what point I will have to absorb, or rather observe, okay. And you select out always the emission maxima, you select out always the maxima, because these are the places where the changes, because these are maxima, right. So, the changes are happening to the most at these places. That is why it will always help you a lot in terms of a signal to noise, because under a given set of conditions at the maximum point you always have the maximum number of photons coming out, and that is where it is going to help you a lot. Is it clear how the stop flow fluorescence studies are done? So, this is how stop flow fluorescence is done, okay. So, if you have a change in fluorescence, you park your detector, you say your detector to take the fluorescence from this wavelength or this wavelength that you decide depending upon the system, and then you monitor the change as a function of time, okay. Now, there is one more thing in this figure. If you look at this spectrum, this blue one, right. If you look at the blue one, what is going to happen is this. The first two, that means the first two spectra, you can see that the lambda excitation, this lambda excitation is 292 nanometers, okay. The lambda excitation is 292 nanometers means I am using the steady state fluorometer, I am hitting the sample with an excitation light which is a wavelength of 292 nanometers. Now, why have I selected 292 nanometers? Can you tell me? We have done this before. To excite only what? Tryptophan, because tyrosine at that place, if you look at the absorption spectrum, has very low intensity. So, that means exclusively you would be exciting tryptophan. So, whatever emission you would monitor is from tryptophan, okay. Now, if you would do the same excitation at 275, here what would happen though is you would be exciting both. That means you would be exciting both tyrosine and both tryptophan. If you would be exciting both of these, now do you realize where this one is coming from? So, this one is your tryptophan peak and this one is your tyrosine, okay. So, for a protein having tryptophan and tyrosine, if you change your excitation wavelength like this, right, and scan for your emission, these are the changes you are going to observe, okay. And that is why people selectively use 290 or 295, so that they can look at tryptophan only, okay, right. So, I think that is pretty much what I had to discuss. You know, there are a lot of other things that can be done with fluorescence. The good thing about fluorescence is very sensitive. You can do experiments with low concentration of samples, right. So, if you would be doing an absorbance, remember absorbance would typically involve taking protein concentration at a very high level, but if you would do fluorescence, fluorescence can be done at very low levels, right. So, micromolar level, little higher micromolar and so on. Now, what it helps is in this. One is obviously your sample consumption is really low, okay, no problem. The other issue is there is a phenomenon known as protein aggregation. Okay. So, if you have very high concentration of proteins, they have a tendency to aggregate. So, that means, if you are doing any absorbance measurements where you need high concentration of proteins, that means you also have a high chance or a decent chance of that protein aggregating for you. If the protein is aggregating, then it is no use doing the experiment, because your sample is already bad. That means, you cannot use the sample anymore for your experiment. Okay. So, your results would not be conclusive, because you also have contribution from protein aggregates. But fluorescence, if you are doing it at say 1 micromolar or 5 micromolar or so, most of the proteins in general, most of the proteins in general would not be aggregating at that lower concentration, and hence you can easily do fluorescence without wondering about this competing process, which can have effect on your experimental data.